para position, para relative to the sp3 carbon. And then we put the plus charge into the second ortho position. This one is a secondary carbocation-like resonance form. This one is about the same. But here, whoops, that's different. Okay? And the difference is that this now is a plus charge that is tertiary carbocation-like. So it's more highly substituted. So this is actually a dominant resonance form. Okay? So we got two reasonable ones and one good one. So this one will be dominating over the other two. Let's now do para, because para is very similar to the scenario. We attack para, and we get again ortho and para plus charges. So here's one of them. Then we move from left to right. There's the other one. And if we move up, there is the para one. That is again different from these two because it's tertiary carbocation-like. So we got two cases, ortho and para, that have two reasonable secondary carbocation resonance forms, plus a really good one that's tertiary carbocation-like. And so now what happens when we attack meta? Attack meta, you go here, and so we get the plus charge here and the plus charge here, the two ortho positions, and one para position. And notice that when you do this plus charge here, you do the allelic transposition. That resonance form bypasses the, as we have seen by these two forms, the good resonance structure that's tertiary carbocation-like. It just has ordinary, so to speak, three secondary carbocation resonance forms. So the bottom line is, all positions are activated. But because ortho and para gives you the extra oomph of a tertiary carbocation-like contribution to the resonance form, those are preferred. So they're more activated. Ortho para is more activated than meta. And here I'm sneaking in again the steric effect. If you put in a T-butyl group here, then in fact ortho is shut down because the T-butyl group is so large. And I made a model of this in the same molecule so you can compare them directly. Up here is tertiary butyl, and down here is methyl. Methyl is not too shabby. Remember that these little puny balls are actually more like oranges, okay, in terms of real van der Waals radius. Okay? So they're much larger. And so they bump into this regional space here, so when the electrophile comes in, and remember it comes in sort of from the top when it attacks, it bumps into this somewhat. But here's the really bad one. Okay? So if you replace all these hydrogens with oranges, then they really impede on attack here. So T-butyl shuts down ortho attack. So you get strong selectivity because of steric effects in many cases. Okay, so what happens with inductive acceptors? And let's look at trifluoromethyl. Okay, so they are deactivate by electronegativity by and large, and so trifluoromethylbenzene is much slower than benzene in electrophilic aromatic substitution. But it's not so slow that it doesn't go. They all go. Okay? And sometimes you have to tinker with these by heating up to force, to accelerate the process because they're reasonably slow. Okay, so we're doing a nitration. Okay? And so we look at the result, and you find that by far the major product is the meta nitro derivative. There's always a little bit of the other guys, so they're close. Okay? So this electronic argument is good, but it's close. Okay? Energetically quite close, but there's a clear preference for meta, clearly synthetically very useful. 91% I take any day for an organic reaction. So this is a deactivator that directs meta, and the question is why? And again, we go through this exercise of going through all the resonance forms and first write them all down, and then you analyze where they differ, where they're the same. Okay? So again, we come in ortho, top line, and you get this plus charge here. Allelic transposition gives you this plus charge here. These are ordinary secondary carbocation structures, as in the previous slide with the activator. But here's the difference. Once you put the plus charge here, that's next to an electron withdrawing substituent. Electron withdrawing means that the substituent wants electron density. The last thing it wants is a plus charge. Okay? So this is really bad. And therefore, this resonance contributor is very poor. Basically, it's out of the picture, meaning that ortho attack really only gives you two reasonable resonance forms to work with. And the same thing happens when you attack para. You come in here, you get a plus charge here on the left or on the right. These are the two orthos. And then the para one has plus charge next to the trifluoromethyl. That's also a stinker. Okay? And you don't want that. And you ignore it. And that means that this attack also only has two workable resonance forms. Now we come in meta, and you know already what's going to happen. Meta, you put the plus charge here. When you do the first allelic transposition to put it para, you're again bypassing the destabilizing group. It's destabilizing with respect to a positive charge. So you get one reasonable secondary carbocation structure, another one, and then the third one is also reasonable. So here we have three working resonance forms that are similar to the ones in the previous slide, and no stinker resonance. Okay? And that means that it's going meta. Now remember, this is a deactivator, so everything is deactivated. But because of this resonance picture, ortho and para attack is deactivated more than meta. So meta wins by default, not because this group activates the meta position. And this is something you have to be very careful about when you use other textbooks or the web. Often the term, so this is a verbage problem, the term is used, electron acceptors activate the meta position. They don't do any such thing. They deactivate everything. Everything is slow. It's just that ortho para is even slower than meta. So by default, the molecule picks the least disagreeable solution. Okay? And that's why it goes meta. So much for induction. So what about resonance? So resonance donors, as I said, are atoms that have an electron pair that can be engaged in resonance. And for all practical purposes, all we're going to see is nitrogen and oxygen. Nitrogen and oxygen. Sometimes when I get bored in an exam, I make it a sulfur, okay? But remember, they're basically the same. Oxygen, sulfur. Sulfur is bigger, but it's got this electron pair also. And sometimes I go from nitrogen to phosphorus. Okay? Rarely. I usually stick with nitrogen and oxygen. And so these electron pairs can be engaged in resonance. And then they activate. And so when we run an experiment, here's a case where the amino group was actually acetylated. That works fine. There's still obviously an electron pair. So substituted amines or the amino group itself doesn't matter. That is the electron pair, and that's what this means here and here and so on. That can donate. Okay? And when you do a nitration at room temperature, you get mainly ortho para. Only a trace of meta. Okay? And in this case, its ratio is 20-80. But remember, again, for statistical reasons, you should get 66% ortho, 33% para, because it's a 2-to-1 ratio of available positions. Okay? And instead, you get 21-80, the other way around. Okay? And that is because this group is reasonably bulky, and the nitronium ion bumps into it every now and then, so it prefers to go para. Okay? So nitration goes at room temperature. This is very fast. Typically, nitration you actually have to heat, even for benzene ring, just benzene itself, nitration a little bit. But this one goes smoothly at room temperature. And in fact, with activating substituents like this, the electrophilic bromination actually occurs without a catalyst. So you don't even need FeBr3. But I'm saying this as an aside because the default position for you should be, I think, to play it safe, just use the catalyst. It can't hurt. It makes it only faster. But it would already occur at room temperature bromination because these benzene rings are now sufficiently nucleophilic that bromine will attack. So now, again, why orthopara? And we are back to the exercise of all the resonance forms. All right, well, let's go through this again. Now we have, because there's a little change here, which explains why these resonance-donating substituents are so powerful. So we attack ortho, okay, that puts a plus charge here. That's an old hat. We've seen that guy before. Then you do the allylic transposition, another plus charge here. We've seen that before. Then we do another allylic transposition. That one actually is not so hot. Why? Because it's got a positive charge next to a nitrogen, which by induction is electron withdrawing. So that's actually a reasonable stinker. Okay? But what overrides everything is the next one where the electron pair kicks in and you make the iminoamine type, the double bond. Okay? And the reason that this is the strongest, by far the strongest contributor, is because it's an octet. So something we didn't really stress enough in the mechanisms of electrophilic aromatic substitution, all the carbocations in the resonance forms that we've written are electron sextets. Okay? They're electron-deficient carbocation structures, therefore relatively high in energy, not happy campus. When you write an octet, that is a huge winner, okay? And it overrides everything else. So this is really in its own league. That's a very strong contributor to the basic structure of the molecule. And you actually see this when you isolate structures like this, that there's a strong C, that the CN bond is shortened because there's a strong double bond character. Okay? So you do the para thing and you get the same result, obviously, plus charge here, that's actually a reasonable stinker, but when you invoke the resonance from the nitrogen, that's again an octet. So ortho and para have some super resonance forms, namely 2 octets. And again, as you've seen before, if you go in meta, you bypass the substituent. And in this case, you bypass a really good substituent. And so you put the plus charge here, and then the next resonance form, you go right past that potentially donating electron pair. You put it here and you put it here. So these aren't bad. But in competition, these are much better. Okay? So again, everything is activated, but ortho and para is more activated than meta. And we can look at the movie for this of the benzene amine. And let me stop it every now and then. So here comes the electrophile. It attacks. And so you can see here, after attack, this guy becomes sp3 hybridized, this one becomes sp3, this one becomes sp3, and the plus charge is then therefore distributed over the remaining frame. And so you get the first positive charges here. It's first here, and then by resonance it moves here. And similarly here, first here, and then by resonance it moves here. This is the one that bypasses this guy. And over here we started here, and then we're moving it up there. And that gives us now this picture and the incipient resonance. Remember, this resonance form is actually not so good. The plus charge next to nitrogen is not good, but the next step, namely donating this electron pair, is really good. So at this stage, we have reached, unfortunately, they're not in sync in that movie, so there's a flaw in it. But this one has the plus charge over here, it has to yet donate this electron pair. This guy, of course, bypasses the amino, but this is the winner in the para situation. And then we're finishing the ortho to generate the other winner. So these two guys are winners, and this guy bypasses the amino function, and so it's not as good. So what happens with resonance acceptors? Well, we know that they're meta directing, they're deactivating. So let's see what we can have. Let's start with benzoic acid or benzene carboxylic acid. You do a nitration, and again, by far the major product is the meta nitro benzoic acid. I forgot to mention, that was already on the previous slide, all reagents that we've seen will attack, as is obvious from the examples, a deactivated benzene ring fine. So you can do halogenation, nitration, sulfonation. The only exception is Friedel-Crafts alkylations. The Friedel-Crafts reagents, carbocations, or their precursors, as shown in the example here, the activated carbon, they're too weak to overcome the deactivation of benzene ring. And so Friedel-Crafts shuts down for electron withdrawing substituents. So if the benzene ring is less electron rich than benzene itself, then the Friedel-Crafts doesn't work. Everything else works. Okay? This will become significant on Thursday when we do a little bit of synthetic strategy. Okay, so mechanism, back to the old permutation of all the resonance forms. So we attack ortho, that puts plus charge here, and then here. When it's up here, the plus charge is next to the positively polarized delta plus, so by induction, that's already bad. And now we can make it even worse by invoking a resonance form in which we have a full plus charge on this carbon, and that's a total stinker, okay? So that's really bad. So these two guys are really bad. You can throw them out. They're not in the picture. So we only have 2 reasonable resonance forms for ortho. Same thing when you go para, because of symmetry, the 1-3 symmetry. So if you attack here, plus charge here, this one is equivalent to that one. That's a poor one, and the real stinker is that one. 2 plus charge next to each other, and here's another reasonable one. Okay? So this one has 2 reasonable ones. This one has 2 reasonable ones. What about meta? Meta, again, we bypass the substituent. Okay? Plus charge here, plus charge here, plus charge here. And so it's got 3 reasonable resonance forms, and meta wins. Again, because it's the least deactivated position. All the other ones are worse. Meta isn't great either, but it's not as bad as the other 2 options. So there's a movie for that. Again, they're not quite in sync, but here's the electrophile again attacking. Here are the sp3 hybridized carbons, here, here, and here. And then the positive charge is delocalized over the entire frame. And here we got the carboxylic acid function. And so we got plus charge up here now. Let's look at these resonance form, plus charge here, plus charge here, plus here. That's they're all equivalent. Then we do the next one, the next set. Oops, I overshot. Here we go. Plus here, plus here. These 2 are equivalent to what we saw before, but here's the first stinker, plus next to the positively polarized carbon, and that's one of the paras. And then we do the next one. That gives you a second stinker now for the ortho, and this one just bypasses it, but so we got plus charge here. And here's the super stinker for the para, 2 pluses next to each other. And then we can do the same thing up here, so there's the super bad one, and and then that one was left behind. So ortho and para have these super bad ones and two others that are not so good, whereas this guy, the meta, has three reasonable secondary carbocation resonance forms, and it wins. So there's always an exception. So far it was pretty straightforward. Donors, ortho, para, acceptors, meta. There's an exception, and those are the halogens, and we'll talk about those after the break. Either I'm running out of power, or it's just a loose contact. Why should it die completely? Or maybe that's what happens. No. Yeah. Okay.
Okay. So for the part where
You gotta go out on the street and some fucks.
Okay, so here is the exception, namely the situation of the halogens. The halogens are inductively electron withdrawing, resonance-wise actually donors, but the induction in the starting material wins out so that halogens are deactivating, okay? Slightly. We'll see some numbers just to calibrate you. But nevertheless, even though they are deactivating, they're ortho para directors. And again, the picture of the resonance forms in the carbocation give you the answer for this. So here we have bromobenzene, and we can brominate it over again if we add more bromine and iron tribromide, and you notice it's ortho para. And again, para dominates because bromine is rather big, so coming in ortho is not as good as coming in para. So why? So let's look again at the resonance, all the resonance forms of attack at the ortho, meta, and para position. So if we come in ortho, plus charge, normal, plus charge, normal. Here's the first one that's unusual. It's a plus charge next to an inductively withdrawing substituent. So that's not good. But again, because there's an electron pair sitting here, this electron pair can donate, and this is great. This is an octet. Okay? So even though in the starting neutral bromobenzene, the bromine withdraws more electron density by induction than it donates by resonance, when it comes to the charged intermediate, the charge really absolutely demands the resonance stabilization, and you get into the octet. It has a chance to form an octet structure. And so the same thing happens when you attack para. This is normal, this is normal, this is not so good, but this is a big winner. Okay? Again, an octet. So the picture is very much like the case of the normal resonance donating substituents, amino and oxygen, nitrogen and oxygen. There's strong stabilization of the intermediate carbocations. It just so happens that the resonance stabilization expresses itself only at the cation stage, not in the starting neutral material. And this is because charge basically